Hi all, welcome to second part of the video lecture on relational data model. See, in the part 1 of the video lecture we covered some of the fundamentals of this relational data model. So like an introduction video, so we saw some terminologies like what is relational schema, what is intension, extension, right? So what about domain of each attribute? So those things we saw. Now let's see the formal definition of relational model. Relation, right? Basically, in relational model, which is a popular representational or implementational data model, right? So here that information is represented in the form of tables, and tables we call as relation. And why we are using this term? So this terminology is something you are already familiar in set theory, right? So now we are trying to relate that basic definition of relation from set theory with the concept of relation here in relational model. See, before this relational modeling, what we have is the popular ER model, which is the conceptual data model, and from there we have a formal mapping to relational model also. Those mapping details, everything we will see later. Now it's time for us to define formally what is a relation. Okay, so you can define it like that mathematically. This relation state, so what is state of a relation, what is schema, those things we already defined. The relation state, typically we denote like a small r of capital R, right? So this capital R corresponds to the structure, that is a schema, relation schema, and small r of capital R means at any time the set of all values in a relation, the state of the relation or extension, right? So it is a mathematical relation, so it corresponds to the mathematical meaning of relation from set theory. Of degree n, okay, and hope you remember what is a relation of degree n. So basically we have a relation of degree 2, which is a collection of ordered pairs. So degree n relation means it will contain ordered n tuples, right? So on the domain, and now relation you will typically define over sets, right? So now in relational this particular relational data model, what you will be taking as a set. The set is nothing but the set of all domains of each and every attribute. Suppose I have n different attribute, a1, a2, etc. an. Each attribute is having a domain, right? And hope you remember what is a domain. We explained in the previous video also. So domain corresponds to set of all possible values for this particular attribute. Similarly, what is domain of a2, etc. What is domain of an? Now each of them is a set, right? Now you take the cross product of these sets. Hope you remember how to take this cross product among sets. And you will get something like so when you are taking something like this, you will get ordered n tuples, right? So from domain a1, suppose I am taking this x1, x2 I am taking from domain of a2, etc. some xn. So it is something like this, as that this x1 belongs to domain of a1, right? x2 belongs to domain of a2, etc. So this is typically, and finally this xn belongs to domain of an. Okay, so now you can relate it with the formal definition of relation from set theory, right? So set theory, we can think of relation as a subset of the Cartesian product. If you are thinking of a relation between two sets, it will be a collection of ordered pairs. Now here we have a relation among n sets, and each set corresponds to the domain of each and every attribute, okay, and it will be ordered n tuples, so where each element of this n tuple is coming from the concerned domain. So this is how you can visualize this state of a relation at any point of time. If you want a more clarity about this point, let me take an example. I may try to explain with a small example. For example, okay, I have a relation, say with the attributes. So this is a typical way I am representing the relation a1, a2, a3. Let's take 3 attribute for the time being, and we have to define domain of each attribute. Okay, so let domain of a1, let it be name of students or people in an organization, something. So let me define them like randomly. I am giving a say a b. Okay, now b b and b a. Okay, something like this. Fine. So domain of a2, let it be age of pupil. Say let me define some ages randomly, 20, 22, 30, 35, like that, okay, or some 36. Now domain of a3, let it be something, what I can tell is a grade of pupils. Say grades are giving names like grade A, grade B, C, like that. 3 grades I am defining, for example. So now what you have to do, so you have to define, so this is your relation, right? So this is your relation R. So I can formally define this relation is having the schema R of A1, A2, A3. So what does I mean by this? So this is the schema in the sense the structure, right? Where we can formally say what is this A1. So it is having a domain, and that is a collection of all names, right? So you can give a data type for it. Similarly A2, so say age information. Okay, so you can relate it meaningfully. So I am just taking some random examples, so you can give some meaningful example here. Okay, so that about it. Now we are going to see what is the state of the relation at any instance. Okay, so let me tell you. So at any point of time, so let me define a particular state as name of the person. Let it be, say, BB is his name. And then this let me use a different color. So this person is having a name BB, and let his age be 22 and his grade be A. Okay, now there is another person, say with the name AB, say age 20 with the grade C. Say there is another person with the name, say BA, with the grade say it can repeat, right, with say same age and say grade B some B. Okay, so it can be anything. So for the time being, this is the current state of the relation. Now how you can relate it with the formal definition of the relation? Relation is a subset of the Cartesian product, right? So at any point, this R of R will be a subset of the Cartesian product, that is domain of A1. So this is one of the set you have to consider, cross product domain of A2, Cartesian product domain of A3. Now what is this? I mean, how can you define this? So this is something like ordered triples. So because we are talking about a relation of degree 3. Okay, so you can see ordered triples here, x1, x2, x3, such that each of this x1 is a value which is coming from the set domain of A1, right? Something like this. And this x2 is coming from domain of A2. And this x3 is coming from domain of A3, like that. Okay, so some of the instances, let me tell you, like so let me take one ordered pair, like AA is name of a person, let his age be 20, then let his grade be A. AA itself with the 20, he can have a grade B. AA itself, age 20, he can have his grade C. Like that you can formally define this, right? And then you can think about this combination. Say AA itself, but age now I am changing to 22, then with the grade A. So like that you can have many information right here. So can you tell me how many, what is cardinality of this bigger set? So this set is actually etc. I'm talking about. So this is the domain of, or simply what is cardinality of this one? That is what I'm asking. Okay. So the if I have a so this is having. So what about the cardinality of this? This. So this one is having a cardinality. So what is this cardinality? Its cardinality is number of elements of this set. This is 4, right? Similarly, cardinality of A2 will be cardinality of this one, and that is 5. Now cardinality of this domain of A3, this set, this particular set, its cardinality is 3. Now what is cardinality of this cross product of these 3 sets? Okay, so that is nothing but, I hope you remember, in this cardinality value, if you are focusing on the cardinality value and I am asking you what it is, so that cardinality will be some 4 into, hope you remember this, right, 5 into 3, because each element from this domain of A1 will be related with each and every element. So we are talking about all combination. It's AA itself, you can have a combination AA20, then ABC, then AA22, then ABC. So like that you can count it, right? So the first element, or you can think like this, x1 can be selected in 4 ways. Say x2 can be selected in 5 ways, and x3 can be selected in 3 ways, right? By multiplicative rule, you can say that the total possibilities are like a 4 into 5 into this many ordered triples are actually there. So at any time you can see a subset of it. So here if you are looking at a cardinality of this particular R, it is just 3 only. In the sense here we have a so what is this R of R here? So this particular state corresponds to the set ordered pair BB 22A. So this is one of the element from this bigger set. Okay, and similarly another ordered pair I am having, that is AB 20C. Okay, and now I have another ordered pair, that is BA 22 B. So this is one of the subset. Okay, so like that you can think of any relational state which is a subset of the bigger set, that is Cartesian product among domain of each and every attributes. Okay, so that about it. Now within so this is an ordered triple. Similarly, you can think of relation as a collection of ordered n tuples, right? So this each such this one row is what we call as a tuple. Okay, so, tuple. So this is something like a 3 tuples. I can say that. So this is a 3 tuple. 3 tuple in the sense I have a tuple or row with 3 elements, and the order matters also, because when I am writing like a BB22A, what I mean is the attribute A1 assumes a value BB, attribute A2 assumes a value 22, and attribute A3 assumes a value A. Okay, so that is very important. Now I just want to tell you few more terminologies. So let me take a different relation. What I can tell, relation, different state of the relation. Okay, so same, I am just taking a different example. So what I am doing, let me take name of the person as BB, then his age be 20, then grade be A, and there is another person with name be A and age be 22 and grade be C, like that. So let it be the small example. So I have a state, you can see that in the table there are 2 rows and these are all the values, right? So you can say that I have a relation with the state. So what about the state of the relation? So there are 2 ordered 3 tuples. Are you okay with this terminology? So this is the first tuple, right? So this is tuple number 1 or tuple number, row number 1, and this is second tuple. So there are 2 tuples. Okay, so 2 tuples. And what about each tuple? They are ordered, right? They are ordered, and what kind of ordering we are having? This is not ordered pairs, they are ordered 3 tuples. So similarly, in general, you can see that suppose this I have a n attribute, right? So this R relation R is having attributes like A1, A2, etc. An, right? Now at any time this relational state of this particular relation schema R will be a subset of the Cartesian product, which is domain of A1, domain of A2, etc. Cartesian product, okay, cross product, etc. cross product, domain of An. Okay, so this is how you will be defining it. See, now you can see this is actually ordered n tuples, right? Because at any time this is something that contains x1, x2, etc. xn, where each xi, so let me write like each xi that belongs to this domain of Ai. Okay, so here this order matters, because if you are changing this order, how you will identify that this x1 is coming from domain of A1 or this x2 is coming from domain of A2. If you are swapping them and you are writing without any ordering, that is not going to convey any meaning, right? It's the same example itself. If you are writing 20 here, it will be interpreted as name of the person is 20 and age is BB. So you are not supposed to swap this. Okay, so this is ordered. So this terminology is important. So you can't change the order. So this is something a standard thing that you know from the definition of relation itself, right? Because it is basically ordered n tuples. The same thing you can see here also. Now suppose when you counted this R of R, see the total cardinality of this one is different, because if you are taking cardinality of this one, this will be cardinality of domain of A1 into cardinality of domain of A2 into etc. So that will be the value. That is a bigger number. But now I am focusing on cardinality of just a state of this particular relation, right? So let me take it as some m. So I am talking about a subset of this whole thing, right? So now what is size of the subset? So let it be m. Now I can say that this R of R contains m tuples. And what kind of a tuple? Where each tuple is ordered n tuple. Okay, so this is important. This is what I was trying to say. Ordered n tuples. So I can say that this particular relation's state is containing m number of ordered n tuples. Okay, so what is this m? The cardinality of the current state. Okay, so it is having this many rows. That is what I mean by m. And each row, if you are focusing, it is containing values for n attributes of the relation. Okay, and it is ordered also. Ordered n tuple. Now I just want to tell you one more thing. Is this ordering matters always? Okay, so if you want, you can change the basic definition of relation, and you can think of something different where order of tuples doesn't matter. So first thing I just want to tell you, it is something like, what about ordering of tuples in a relation? Okay, ordering of tuples in a relation. So I have a relation state R. I can say that the first tuple is something like a BB, say 20A, and the second tuple is something like say BA 22 and C, and the third tuple is something like AB say 20 so whatever it is, say grade B. Okay, so like that. Now so this is according to me, this is the first tuple, second tuple, or third tuple. So can I write the same thing as, let the first tuple be say AB 20B, okay, and the second tuple be say AB so that is what I written, sorry, second tuple be BA 22C, and the third tuple be BB 20A. See, this is also same. Okay, so that means relation is basically a set. It's actually set in the sense it's a subset of the Cartesian product, right? So basically it is a set. So as a relation is a set, right? Relation is a set of tuples. Set of tuples. What kind of tuple? Each tuple is ordered 3 tuples. Here you can see. So here I have a set of tuples. Okay. So within a relation, order does not matter. Does not matter. Whether you written like this is a first tuple or this is a first tuple, both are same. Okay. But look at a tuple. I mean, so in a relation, order doesn't matter. So basically relation is an unordered collection of tuples. So let me say it more formally like this. Relation is an unordered collection of tuples. Now what about a single tuple? If you are looking at a particular tuple, order matters, right? Order matters. So it is basically ordered. So tuple is nothing but ordered n tuples. And what is this m? N is the number of attributes of the relation. Okay, so that is the first point. So within a relation, you can see it is a subset of the Cartesian product of the domains. So as it is a set, order doesn't matter. You can write this as a first set or this as a first set, like that. Any order is possible. And also if you want, you can give a formal ordering also, depending on the user requirement. For example, the same table, suppose the same table R of R, the user wants to order with respect to the first attribute A1. You hope you remember attribute A1 I assumed like a name of the person, and A2 was the age, and A3 was the grade, something like that. Okay, so if you so I'm trying to give a meaning to these things. So A1, what I mean is name of people, okay, and A2 I mean say age, and A3 I mean their grade something. Okay, so some random example I taken, but still I am trying to give a meaning. So user wants some ordering with respect to the attribute A1. Now see, this is the correct result, right? With respect to AB, this I mean then with respect to the attribute A1, which is name, I am ordering them like so that AB will come first, then BA, then BB. Okay, now order matters. Why order matters? Because the user from the user point of view, he needs a order. Okay, so in that case, typically usually when you study this SQL queries and all, you will see a special command from the user. He will write like order by A1. So if he is writing a query saying that order by A1, so the system will order the entire relation with respect to the attribute A1. And if you want, you can order the tuples of the relation with respect to more than one attributes also. So all these things are fine, but it is from the user. But by default, no ordering. Okay, so by default no ordering. Okay, no ordering. But if the user want, you can give an ordering, right? No ordering. So this is what I want to highlight. Okay. Now the second thing is, by default tuple, if you are focusing on a single tuple, it is having an order, right? So by default tuples are ordered. I mean, within a tuple, the elements are ordered. Because, you see, if I am writing like this, like R of R is equal to A20, grade A, etc. So what I mean is, this corresponds to the attribute A1 or name of the person, this corresponds to age, and this corresponds to attribute A3 grade. So I have a meaning now. So if I am changing the order, I am losing this meaning, right? So I don't want it. But at the same time, you have an option. If you want, you can make them also unordered, right? So how tuples can be unordered? Something like that, okay? Unordered. So what you can do is, you can define them in such a way that at any time, so what I am saying is, I am relating that tuple value with the attribute name, then there is no issue, because I am saying that this A1 is having a value A, and then A2 is having a value 20, and A3 is having a value capital A. If I am writing like this, etc., other tuples will come like that. Then this is same as I can change the order, like I am saying that A2 is having a value 20. Now it is clear, you don't have to worry like how it will relate, because it's clearly saying that attribute A2 is having a value 20. Similarly, attribute A1 is having a value A, then A3 is having a value A. So you can write them in any order. Okay, now order doesn't matter. Okay, so if you are using this kind of a convention, order doesn't matter. But by default, the standard definition of the relation is saying that within a tuple, order matters. But if you want, you can have a, so this is this is not the basic definition. I can say that this is an alternative definition of relation. Okay, so if you want, you can have this kind of an option also. This is the whole thing I want to tell you. So now you can see things in a more formal way. You know, relation is a subset of the Cartesian product, say domain of A1, etc., domain of A, and the Cartesian product specifies all possible combination of the values from the underlying domain. Okay, hence, if we denote the total number of values or the cardinality of a particular domain by this symbol, you know this, right? The cardinality, you can see that the Cartesian product, this whole thing, or the universal relation, something like that. Okay, it will contain all elements, right? All possible combinations. So it will be having a cardinality of domain of A1 into, hope you remember, I taken small examples for that, like this 4 into 5 into 3. Okay, so that is what is explained in a general way. So at any time you will get a cardinality which is at most this. Okay, so because it is basically a subset. So this product of cardinality of all domains represents the total number of possible instances of tuples that can exist at any state R of R. So this R of R can go for a maximum of this many number of tuples, but at any time you will have a very small number in your current state. So all of these possibilities, a relation state at a given time, or this is what we call as the current relation state, reflects only valid tuples. So all this this many number of valid tuples we are having. But if you are thinking of something beyond this, you are taking A1 is an attribute, say name of the person, so it is having a formal domain. So domain is very important. So if you are taking something that is outside domain, now you are having an invalid tuple, right? So that makes the entire relation state invalid. So with respect to the real world, you always make sure that it is following this definition, otherwise you may not get a valid relation state. Yeah, that about it. Now I hope this example is clear. or you can take your own example and you can try to visualize what this formal definition means. Okay, now some of the characteristics of the relation, ordering of the tuples in a relation. This is what we've seen, that also I explained. Like within a relation is basically a set, or it's a subset of the Cartesian product, so it's basically a set, right? So in a set, order doesn't matter, you can write the tuples in any order, so by default, right? So relation is basically a set of tuples. Mathematically, elements of a set have no order, right? Hence, the tuples in a relation do not have any order. In other words, the relation is not sensitive to ordering of the tuples. Or not sensitive to ordering of the tuples. So, tuple ordering is not part of the relation definition, because the relation attempts to represent the fact that the default meaning it is trying to convey. So, but many tuple orders can be specified on the same relation. So, that is from the requirement of the user. If needed, you can give a tuple ordering, right? For example, the tuples in the student relation, say, can be ordered by. So, this is what I was trying to say, ordered by, say, name. So, then the elements will be stored with respect to some ordering of the name, right? So default ordering, increasing order, like that. Or you can order by SSN, or if you want, you can order by age or some other attribute, or you can think of a combination also. Those things and how it will react when you are giving a query like order by, we will see when we are discussing SQL. So when a relation is implemented as a file or displayed as a table, a particular ordering may be specified on the records of the file if needed. Otherwise, by default, it's not following any order. Similarly, what about ordering of values in a tuple? That also by default ordering must be there. But if you want, you can think of an alternative definition by which you can skip this ordering. So just read it according to the preceding definition of the relation. An n tuple is an ordered list. So by default, when I am saying that ordered n tuple or n tuple, it is an ordered list of n values. So the ordering of values within a tuple and hence the attributes of the schema is important. So this is the default thing. Okay. Now, however, at a more abstract level, if you want, you can think of a different way of this. The order of the attributes and their values is not that important as long as the correspondence, so this is important, correspondence between them is maintained. An alternative definition of a relation can be given, making the ordering of values in a tuple unnecessary. So this is something that corresponds to an alternative definition. So in this definition, a tuple can be ordered as a set of something like attribute value, like that I have to mention. So hope you remember. So this is what I was trying to say. So this one, so every time you have to mention the attribute as well as value, attribute as well. So in that, if you are writing like that, you can skip the order because that correspondence is there. Okay. So if you are writing like this, so this mapping of every attribute you are trying to map with a value, and that description, so it is something like a self-describing data, right? So each data is describing, AA is describing itself, that I am name of a person, like attribute name. When I am associating, I am trying to describe this data. So if I am simply writing this, it is of no meaning for a third party, right? So when someone is looking, what is this AA, he don't know. But when I am relating like A1, AA means AA corresponds to the attribute A1, so it is having a meaning, right? Yeah, that about it. So now the data is trying to describe itself because the description of each value is included in a tuple. So some example they are given. You can take a simple example like what I told you already. So here it's saying like, so I think in my example I put like this. You can use that notation or this notation, fine. So here they are using comma for separating. Name is Dick Davidson. SSN is this one, home phone. So if you are writing like that, you can skip the order, like I am writing address now first. So say same thing only, same address, everything, but I am just changing the order within a tuple. I am changing the order, right? Because I am having this kind of a correspondence. That's why. So hope you got it. Now another thing is like again some of the characteristics of the relation. What about its values and nulls in the tuple? So by default, any relation, you look at any tuple, the value of an attribute should be atomic. Okay, so it should not be further divisible. Each value in a tuple is an atomic value, that is, it is not divisible into components within the framework of the basic. So basic relational model says that the value should be atomic. Okay, so that means it's very important. The composite and multiple multi-valued attribute. You know what is a composite attribute? It can divide further. Multi-valued means so it can assume more than one value corresponding to each tuple, right? Corresponding to each attribute within a tuple. Yeah. Anyway, something like that is not allowed in relational model. ER model, we saw both of them because ER model is something closer to the user. When it comes to implementation, if you allow composite or multi-valued attribute, that will make things complicated. So the basic relational model is having an assumption they are not going to support composite attribute or multi-valued attribute. Okay, so this model is sometimes called as a flat relational model or the basic relational model. So they are not going to allow these two things, and much of the theory behind the relational model was developed by this assumption in mind. For example, this normalization we will see later. There are different ways of standardizing this relational model, like first normal form, second normal form, etc., and where this first normal form is having this default assumption. So from that point they are thinking of other things and all. So anyway, in relational model, especially if it is trying to have a normalization, say first, if I'm saying that a relation is in first normal form, definitely it should not contain any composite or multi-valued attribute. Now what you will do with them? So the multi-valued attributes must be represented by a separate relation, and we will see how this can be do. In ER model, definitely we have a multi-valued attribute, but when you are mapping that ER model to relational model, map each multi-valued attribute to a different relation. Don't put them inside some relation for which it is part of it, for which I mean every entity we will map to a relation, and that time this if that entity is having single valued attribute, map them as the attributes of that particular relation. But if the particular entity is having a multi-valued attribute, that for that attribute alone you have to give a separate table. Okay, anyway, we will see this with example, and it's not simply giving a table. You have to define some relation between. So you have to link this multi-valued attribute with the actual entity, right? So some way that referencing should happen. Some foreign key, those things we will define, and then only this concept will be clear for you. So at this point, don't worry much, and just understand that whenever you are having a multi-valued attribute in the ER diagram, for that multi-valued attribute alone, you maintain a different relation or table. Okay. Now we will add some more attributes to make it relate with the original base, I mean the parent entity, that we will see later. Okay. And similarly, how you will be dealing with the composite attributes, just split them, because composite attributes, say address or something, it can be decomposed further, right? So decompose it, and for each of the subunits, maintain it as a separate single simple attribute. Okay. So composite attribute you divide, and each part you maintain as a separate symbol attribute. Multi-valued attribute you have to maintain a separate table. For composite attribute you just add it in the original table itself, but after dividing it. Okay, so don't make it as a composite attribute. So these two things are not supported by a basic relational model which is having this first normal form. So first normal form, if I am saying by default the relation is not having any composite or multi-valued attribute, so it's also called as a flat relational model assumption. Okay. Now what about the null value? So null values are there, of course, if a particular value of an attribute is not known to you, like it's unknown, or it's not available for the time being, or it's not applicable for that particular attribute. So some examples, everything we already saw in the when I discussed that ER model. Anyway, more examples, practical examples we will see. Sometimes for maybe degree of a person, some people may appointed to a given post without holding the relevant degree, right? So he may not be having a degree, something like this. So that degree field is something not applicable to him, like that. And sometimes say mobile number, something this particular person is having, but he forgot, or so it's not available for the time being. Okay, something may not be applicable to him. It may be unknown whether he is having it or not. So like that, there are different situations by which if you are not able to find a value for an attribute in a tuple, give it a value, special value, null value. So this special null value is supported by relational model. Composite and multi-valued attributes are not supported by relational model. See the context where we are applying null value. Okay. Now the characteristics, one more thing, the interpretation or meaning of a relation. So this is something how you can relate it with the first order predicate logic. Okay, anyway, if you remember it, it will be easy. Otherwise you don't worry much. This is another way of visualizing this relation. Okay, so the relation schema can be interpreted as a assertion, right? And the values are nothing but the facts. Okay, the schema is a assertion, and the values are nothing but the facts which are having this assertion, I mean which are holding this assertion. For example, the schema of the student relation asserts that in general a student entity should have a name, some SSN should be there, home phone number, address, office phone number, age and GPA. This is an assertion I am having. So this is a requirement I am having. Now if a particular tuple follows it, right, so I can say that it's a fact that is keeping this assertion, right, something like that. So each tuple in the relation can be interpreted as a fact or a particular instance of this assertion. So fact in the sense it is satisfying this assertion. Okay, that about it. That is one way. Now an alternative interpretation of the same relational schema is interpreting it like a predicate. And you know what is a predicate from first order logic, I hope so. So where the values in each tuple are interpreted as values that satisfy the predicate. Okay, so we can think of any predicate, and at any time the values of that particular relation will be the tuples which satisfy the predicate. Okay, so if in the sense tuple should be valid. A valid tuple in the sense it should come from the domain, right, for each attribute, and in that case it will be satisfying the predicate, right. So that about it. An assumption called closed world assumption. So this is another terminology. So it's not so important, but at the same time some different ways of interpreting the relation, that's all. So it states that only the true facts in the universe are those which present in the extension of the relation. You know what is extension or state of the relation? Set of possible value at any current. So currently what are the values hold in a given relation is what we call as a extension or the state of the relation, right. Intension is a structure. So look at the extension. You can see that it contains only the true facts. Okay, so that satisfies the predicate. If you are adding some fact which is not satisfying the predicate, that is nothing but the relation, that makes a state an invalid state. So for a valid state this should be true. So this is the requirement for a valid state. If it is so the other combination of the values that makes a predicate are false, and that is not part of the particular relational state. If so, it will make it a invalid state. So we don't want it, right? Yeah, that about it. Thanks for watching.